In OFDM systems, carrier frequency offset estimation and correction is essential in order to maintain orthogonality between the carriers. And also it is very interesting in the sense that OFDM systems can tolerate a carrier offset between the transmitter and the receiver. Here we show the tolerances both in terms of carrier frequency and symbol clock frequency tolerance as specified in the 802.11a specification. The center frequency on the transmitter, for example 5.2 gigahertz as an example carrier, the transmitted center frequency tolerance is 20 plus or minus 20 parts per million maximum. And the transmit center frequency and the symbol clock frequency have to be derived from the same reference oscillator. We'll show this in a diagram next. In fact, the carrier frequency, for example 5.2 gigahertz, has to be derived from the same clock that is used for the symbol timing. Also, the symbol clock frequency tolerance is plus or minus 20 parts per million maximum. And again, they're derived from the same reference oscillator. If you consider a carrier at 5 gigahertz and plus or minus 20 parts per million and take the extreme case between the transmitter and receiver, that translates to about 200 kilohertz possible carrier frequency offset error between the transmitter and receiver. Here on the left we show the OFDM transmitter and the radio. On the right we show the OFDM receiver and the receive radio. In the diagram, the crystal oscillator is at 40 megahertz and it is shown connected to the radio. So the carrier frequency is derived from the 40 megahertz crystal using a synthesizer. And also we show that the 40 megahertz is fed back into the OFDM transmitter in the digital domain and is used in all the timing for the generation of the OFDM symbols as per the requirement of the standard. At the receiver, we also show that the 40 megahertz clock is connected to the radio and drives the synthesizer again. And the 40 megahertz, again from the oscillator, is hooked up to the baseband digital OFDM receiver and is in fact used in the sampling of the ADCs and in symbol timing within the baseband processor. And as per the standard, there could be a tolerance of plus or minus 20 parts per million. And if you take the extreme case between the transmitter and receiver, that's about at 5 gigahertz, that's about 200 kilohertz potential carrier offset that the receiver needs to estimate and correct for. In the following, we will go over the mathematical derivations that lead to an algorithm for the estimation of the frequency carrier offset and also the correction of the carrier frequency offset. Carrier frequency offset in the time domain is shown over here. It can be represented by e to the j 2 pi delta ft, where delta f is the carrier offset, and this is continuous time. If we sample time at equal intervals delta t at a sampling rate of f of s, for example for 802.11a 20 megahertz, then delta t equals 1 over f of s, and each sample time is of course a multiple of delta t, and n represents the sample time, so t sub n, the time instances where we sample, is equal to n times delta t, or n over fs. So we substitute for t the sample time t sub n, and we get the expression in discrete time for the carrier offset as e to the j 2 pi delta f over fs times n. And this is nice because the ratio between the frequencies, of course, is dimensionless, and we have the time index. Here we show the OFDM receiver. This is the RF radio front end, the analog to digital converters, both for I and Q. We show a block for packet detection, AGC control, DC offset estimation, and also feedback from AGC back into the radio in order to correct for gains. If you have high SNR, for example, you need to peel off the gain. We also detect the packets and do coarse carrier frequency offset estimation and fine carrier frequency offset estimation, which we'll discuss. After packet detection, assuming that we have correct timing, at this point we have the received symbols x of n, but they exhibit a carrier offset 2 pi delta f over fs n, which is the carrier offset between the transmitter and receiver, which, as we pointed out, for 802.11a can be up to 200 kilohertz. So delta f can be 200 kilohertz, f of s is 20 megahertz. The idea is that through single processing, we can estimate delta f by an estimate delta f and generate the sequence e to the minus j 2 pi estimate of delta f over fs times n. And carrier offset correction is simply using a complex multiply between this term and the input sequence. And if delta f estimate equals delta f, then the exponentials being, of course, the same base, these two add up and cancel each other out. So it's very straightforward. All we need to do is estimate the carrier offset, multiply it, multiply the complex exponential, which is the carrier offset correction, times the input sequence, and we remove the effects of the carrier offset and recover the original OFDM symbols without carrier offset. Of course, this multiplication times the exponential here is in practice implemented with a real part and imaginary part with a sine and a cosine with index n, and this of course can be easily done with a Cordic block, and we'll talk about that a little bit later. What we are interested in is how do we process the preamble in 802.11a in order to be able to estimate the delta f, the carrier frequency carrier offset. So we're interested in what is going on over here in the carrier offset estimation, so that then we can apply the correction and remove the carrier offset from the signal. After the carrier offset has been removed, then we can remove the guard interval, perform the forward FFT, and of course do pilot tracking. We do the demapping. We also show a connection between the channel estimation and demapper, de-interleaver, depuncture, decoder, and descrambler, and we cover the original bits that were transmitted, the original message. The algorithm that we will use for the estimation of a carrier frequency offset is by Paul Moose in a paper that was published in 1994, A Technique for Orthogonal Frequency Division Multiplexing Frequency Offset Correction, in the IEEE Transactions on Communications. The idea exploits the fact that we send two symbols that are exact replicas of each other, S1 and S2, and both have n samples. In 802.11a, n could be either 16 or 64. So we have, for example, for the long symbol, 64 samples, and the long symbols are a duplicate of each other, and they're sent right after each other in time. Consider this block over here. The time domain OFDM symbol, x of k, once it is transmitted and demodulated by the front-end radio at the receiver, exhibits a carrier offset, either to j2 pi delta f over fs n, which we showed over here. Basically, it's a continuous time carrier offset, but in the discrete time domain, represented discrete time domain. So we have the discrete samples from the transmitter. We're adding carrier offset due to the offset between the transmitter and the receiver. The symbols go through a channel, and we're showing that the channel is represented by the frequency domain h sub k. We receive the symbols r sub k in the time domain. Of course, we add noise, and we have y of k, which is available for processing in order to estimate the carrier offset, frequency carrier offset. Now we'll go through the math step by step so that everything is very clear. X of k are the carriers. For example, we have 48 carriers plus 4 pilots, 52 carriers. Of course, some of the carriers are null, the guard intervals, and we have 64 carriers total that we perform an inverse FFT on to arrive at the time domain OFDM symbols that are transmitted. Of course, a guard interval is a cyclic prefix is added, and they're transmitted. We're not showing the cyclic prefix. This mathematical expression here is just the inverse Fourier transform of the complex carriers X of k. We have n sample FFT, where n is greater or equal to 2k plus 1. And we're actually showing the index going from minus k to k instead of the typical 0 to n. And xk represents the kth carrier. Now as we transmit this sequence in the time domain, as we transmit it through the channel, at the receiver we receive R sub n. And this is without noise at this point. We'll add noise in the next step. So R sub n is what we receive at the receiver, and it's the original sequence X of n that has carrier frequency offset over here, e to the j 2 pi delta f over fs n, because of the difference, because of the carrier offset between the transmitter and receiver. Also, each h sub k gets multiplied by h of k, which is a frequency response at the kth carrier due to the channel. So if you take the channel's frequency response at the kth carrier, the complex number is h of k. So this is where you can have fading. This is the received signal represented mathematically. Now, if we take the term due to the carrier offset, and we have a common base here, so we can add these two together, and we do some factoring, we can represent R sub n as follows. 1 over n, the sum from minus k to k, x of k the carrier, the channel, times e to the j 2 pi n k, which we had over here, and plus delta f over f sub s n divided by n. So here we multiply the top by n and the bottom by n, and then factor out the terms, and that's where we get the n over here, capital N. Now here's a key definition. We are going to define the carrier offset ratio epsilon as equal to delta f over f of s times n. Now this is what we're going to define as the carrier offset ratio, and this is what we want to estimate or talk about mathematically when we talk about carrier offset estimation, which is equivalent to estimating delta f. So substituting for epsilon, we obtain this expression here for the received time domain samples, exhibiting both the effects of the channel per carrier and also the carrier offset expressed as epsilon. Let's denote f sub c as the carrier spacing, the spacing between carriers, and obviously that's equal to f sub s over n, where f of s is the sampling rate and n is the size of the FFT that we used. So we have 64 points for the FFT. F of s could be 20 megahertz. So f sub c would equal to 20 megahertz over 64, or 312.5 kilohertz for 802.11a, for example. So epsilon, in fact, is the ratio delta f over the carrier spacing. If we go back here, we have epsilon equals delta f times n over fs, or delta f divided by fs divided by n, and fs divided by n is the carrier spacing. So epsilon is very interesting. It's the ratio of the carrier offset to the carrier spacing. Now the algorithm depends on sending two symbols, S1 and S2 in time, such that S2 is a replica, a duplicate of S1, each having n samples. So if we take the reception of S of 1 that was transmitted, we receive R sub n, and at the receiver we perform a forward FFT on R sub n, a 64-point forward FFT. If we go back to the block diagram, we'll see that we perform a forward FFT in order to obtain the carriers. So using the forward FFT, we compute the complex samples R1 of k associated with the first symbol, k ranging from 0 to n minus 1, 64 carriers. So we take the input sequence, 64 samples, perform a forward FFT, and this is the expression we get for R1 of k. Now R2 of k is equal to R sub n, except that now we have a time shift of n samples. So the index, instead of going from n equals 0, starts from n equals to n to 2n minus 1 because of the time shift. And of course, since it is exactly a duplicate of S1, then we still have R sub n over here. Now if we take R sub n, which is this expression here where we have the channel effect and the carrier offset, and we substitute for n plus n advancing, then substitute for n in this expression, substitute instead of n plus capital N, and you get this expression between R sub n plus n and R sub n. That is R sub n plus n equals R sub n e to the j 2 pi epsilon. And the way you get that is when you substitute n for n plus n, multiply terms, you'll get a 2 pi k term because the n term cancels out with the bottom n, which is always going to be equal to 1. And other terms, and if you arrange everything, you'll finally come up with this expression over here. You will have a term n epsilon, then divided by n, you'll have 2 pi epsilon, and that's a constant. It doesn't depend on any of the indexes, k or n, and comes out of the summation, and that's what you have over here. This is very critical. And this makes sense. This just says that if you have carrier offset, then the second symbol will be rotated compared to the first symbol by an amount related to the carrier offset. Now the receiver will receive R sub k plus noise. And if we compute the Fourier transform, forward Fourier transform of R sub k, we get Y1 of k. And of course we get R1 sub k from before, plus the Fourier transform of the noise. Now this is for the first symbol, and we get Y2k for the second symbol, and k indexed from 0 through n, the size of the FFT. So k would be from 0 to 63 or 64 points. So you have 64 points for Y1, 64 points for R1 of k. And of course you have 64 points for R sub k. So this is the operation of the forward FFT on Y sub k. This is the operation of forward FFT on the second symbol. But note that due to this relationship we have here, R sub n plus n is equal to R sub n times e to the j 2 pi epsilon. We actually get that Y2 sub k is R1 of k times e to the j 2 pi epsilon here. So in MOOS, a maximum likelihood estimation of epsilon hat is obtained using this formulation where we have Y1 of k and Y2 of k with additive noise. And given that we receive and obtain these values, he derives a maximum likelihood decoder to estimate epsilon hat and obtains this nice compact expression over here. And I will refer you to Moose's paper for the derivation of the maximum likelihood estimation. But I'll show you quickly why this yields the correct estimate of the carrier offset. First of all, the operation involves taking Y2 sub k times the conjugate of Y1 of k. We have 64 of these samples. These are the output of the FFT. So we take them and multiply them times the conjugate, and take the imaginary part and separately sum all 64 imaginary parts together. We have a real number here. We take the real parts and sum all the real parts, all 64 of them, and we have a real number here. We take the ratio and take the inverse tangent or the arctangent and divide it by 2 pi, and we get epsilon, which is our goal, is to get the estimate of the frequency carrier offset. So to show you how this is intuitive is to pay attention to the following. If we assume there is no noise in the channel, so ignoring the noise term n sub k, then Y2 sub k times Y conjugate of Y1 of k, which are these terms here, but now we don't have the term W1 of k and W2 of k. Then we just multiply these terms together times a conjugate, and we get R1 of k, which is a complex number, times its conjugate, so we get its magnitude squared over here, and we get e to the j 2 pi epsilon here. So these terms are equal to this term here, which is a complex number. Now let's take this term and apply it to the formula over here. So if we take the real part of this term, now notice this term does not depend on the indexes, because R1 of k itself is always equal to 1 because we're using the long symbol. In OFDM or 802.11a, the long symbol in the frequency domain, its magnitude is always 1 because it is used for channel estimation. So assuming that we don't have a dependence on the index k, and this is a constant, then each term would be equal to sine of 2 pi epsilon, and we have 2k of these terms that we add them all up, and we get 2k sine of 2 pi epsilon for the top part, the numerator. In the denominator we get 2k, because it's the real part, cosine of 2 pi epsilon. And obviously sine over cosine of 2 pi epsilon is tangent to 2 pi epsilon. The arctangent of tangent 2 pi epsilon is 2 pi epsilon. The 2 pi's cancel out, and we're left with epsilon. So in the case of high SNR or no noise, this equation here yields the estimate of the frequency carrier offset operating only on the basis of having two symbols, n samples long, that are duplicates of each other and sent consecutively. So this in a nutshell is the algorithm for estimating carrier frequency offset. And once the estimation is done, so this block here performs that operation, and we'll show the implementation shortly. We estimate delta F, and then we go through this rotator here where we multiply the samples by the complex exponential 2 pi delta F Fs over n with a minus to cancel out the carrier offset. Of course, when we have noise, the estimate delta F won't exactly equal delta F, and you will have a residual carrier offset, and we'll talk about the impact of that on the system performance and how pilot tracking can tackle that problem. So again, using the fact that in the preamble we have symbols that are duplicates and follow each other in time and have the same length, we can actually calculate what the carrier offset is, an estimate of the carrier offset, and then cancel it out using this operation. Prior to the carrier offset correction, of course, due to the carrier offset, the OFDM carriers lose all orthogonality, and there's a intercarrier interference. Here we show the implementation, a possible implementation of the carrier frequency offset estimation algorithm. We have two symbols coming in, Y1 and Y2, which are duplicates of each other, each n samples long. We take them through an FFT block. First we compute the FFT of Y1, and we conjugate it and store it in a register. Then we compute the FFT of Y2. Then we take the terms one by one and multiply them. And this is this operation right here. We're obtaining Y2k times Y1k conjugate. Then we split them into the real part, imaginary part, accumulate all the real parts and all the imaginary parts, compute the arctangent, do some scaling, and we recover delta F estimate. Now the arctangent can also be implemented efficiently using a quartic algorithm, the quartic arctangent. For example, see the following paper by the folks at IMEC, which is a scalable digital OFDM transceiver published in 2001, November 2001. Now, since multiplication in the frequency domain is convolution in the time domain, and the fact that we are conjugating, we're performing a cross correlation in the time domain, then we can avoid using the FFT and perform the operations in the time domain. So again, we have time domain sequences Y1 and Y2, which are duplicates of each other. Each of them n samples. We delay by n samples, conjugate one of the samples, and multiply them on a sample per sample basis here. We split them into the real part and imaginary part and accumulate the real part, accumulate the imaginary part, compute the arctangent, do some scaling, and we arrive at the estimate of the frequency carrier offset. So depending on your architecture and hardware, you may elect to go either to use the frequency domain or the time domain estimation of the carrier frequency offset estimation. It is also instructive to look at what the effective additive noise is on the carrier offset estimation. So in Moose's paper, he computes the expected value of the estimated carrier offset minus the carrier offset squared, so the variance, and he also shows that his algorithm is a unbiased, so we're showing that as sigma epsilon squared, and that is equal to 1 over 4 pi squared n times n0 over EC. Now this is a very interesting formula. There's a lot of interesting results out of this formula. First of all, some definitions. N0 is the one-sided spectral density of the additive white Gaussian noise. So this, of course, depends on the signal noise ratio. E sub c is the energy of each subcarrier. So E sub c is the energy of the carrier, and therefore this is sort of related to the inverse of the signal to noise ratio. So the variance is related inversely to n, the size of the symbols. So in order to reduce the error of the carrier offset estimation, you would like to use longer and longer symbols. So in 802.11a, for example, we use the long training symbols, which are 64 samples long, so n could be 64. And the larger n, the smaller the error. And that's why those are used for fine carrier offset estimation. If we have more noise in the channel, then obviously we're going to have more error in our estimation, and that would lead to a deterioration of performance. So this equation makes a lot of sense, and it has a lot of implications, as we will discuss, because in 802.11a we have to go through a two-step process. Using the short symbols, we have to do a coarse carrier offset estimation and correction, and then using the long symbols, do a fine carrier offset estimation on the residual carrier offset and also do the correction. This equation also shows that we are always going to have a residual carrier offset when we have noise, and for a long packet that residual carrier offset will cause the carriers to lose orthogonality, and we would have a deterioration in performance. And that's why it is very necessary that the pilot tracking algorithm be active during very long packets in order to compensate for any residual carrier offset. And that in fact happens in practice. The pilots can actually track the residual carrier offset and correct for it, even though the noise is high. Here we show the preamble for 802.11a. Recall that the preamble can be thought of as made of two parts. One are the symbols, the short symbols, which there are 10 of, each 16 samples. And the other part is the long symbols, shown here as T1 and T2, where they are, T2 is an exact copy of T1. The guard interval is 32 samples. The long symbols are 64 samples long, whereas the short symbols are 16 samples. During packet detection, the short symbols are processed in order to obtain an estimate of the coarse carrier frequency offset, and then the long symbols are processed to obtain an estimate of the fine carrier frequency offset. It should be noted that Moose's algorithm can estimate the carrier offset up to half the carrier spacing, which for 802.11a is 312.5 kilohertz, and this has to do with the fact that the arctangent is valid from 0 to pi. For long symbols, we have 64 samples at 20 megahertz, so the carrier spacing is 312.5 kilohertz. Therefore, the long symbols can estimate and correct for carrier offset up to around 150 kilohertz, as shown here. For 802.11g, that's fine because the carrier is at 2.4 gigahertz range, and the tolerance plus or minus 20 parts per million allows for a carrier offset which is less than 150 kilohertz, and therefore in 802.11g we do not need to use coarse carrier frequency offset estimation. We can actually estimate the carrier offset with the long symbols and then use that estimate to remove the carrier offset. In the case of 802.11a, where the transmit carrier frequency is, for example, 5.2 gigahertz, then potentially we have a carrier offset around 200 kilohertz, and we need to do a two-step process. As we show here, the short symbols are exact copies of each other, so we have two symbols following that are duplicates, so we can use these symbols in order to obtain an estimate of the coarse carrier frequency offset. Now, since the short symbols are 16 samples long, at 20 megahertz, their carrier spacing is 1.25 megahertz. So using the short symbols, we can actually obtain a coarse carrier offset estimation up to 625 kilohertz. This diagram shows the operations that are required in 802.11a in order to estimate the coarse and fine carrier frequency offset and to cancel out the effective carrier offset between the transmitter and receiver, and to eliminate inter-carrier interference and loss of orthogonality between the carriers. Shown here, we receive the OFDM symbols, and at first we receive the short preamble. We take two of the short symbols, and using, for example, Moose's algorithm, we can estimate the coarse carrier frequency offset. Once we estimate the coarse carrier frequency offset, then using the rotator here, set with the coarse carrier frequency offset as a frequency, we operate on the incoming OFDM samples, the complex samples, and remove the component due to the coarse carrier frequency offset. We're left with a residual which will be in the range below, in fact below 150, so that the fine frequency offset estimation using the long symbols can estimate the residual carrier offset, and then we've canceled out the effect of carrier offset. So at this point we removed the coarse carrier offset, and we have a residual carrier offset that we use the long symbols in order to estimate the fine carrier offset. Then we use that in the rotator, program that into the rotator and as the frequency, and we eliminate the residual carrier offset, and then these symbols are then passed on to the forward FFT. We should point out that the long symbols also, after they're used for fine carrier offset estimation, the residual carrier offset, the fine, should be eliminated from the long symbols as they are stored so that they can be used for estimating the channel and then channel equalization. The hardware implementation would be different than what is shown here in order to reduce the complexity. This diagram illustrates the operations that are necessary in order to estimate the carrier offset and eliminate it in 802.11a. In this slide we present simulation results. In an end-to-end OFDM simulation, both the transmitter and the receiver with a multipath channel carrier offset, complete acquisition including packet detection, coarse carrier offset estimation and correction, and fine carrier offset estimation and correction. In this case we're simulating 1,000 bytes. The first plot we show the scatter diagram for the constellation, and in this case the carrier offset is very small, but just to illustrate the rotation, it was set at 1 kilohertz. So here the carrier offset correction was turned off, and we see the effect of even a small amount at 1 kilohertz carrier offset on the constellation. There is manifest inter-carrier interference, and of course it is impossible to demodulate. The scatter diagram on the right shows the demodulated constellation, but with the carrier offset correction turned on. So we're estimating the 1 kilohertz carrier offset and applying the carrier offset correction, and we see that the constellation is now correctly demodulated and inter-carrier interference has been eliminated. Here we see the scatter diagram of the pilots with no correction at 1 kilohertz, again illustrating the rotation of the pilots due to the carrier offset, in this case a small amount of 1 kilohertz. As we mentioned before, Even if you perform carrier offset estimation with coarse and fine, with the long symbols, there is a residual carrier offset when you have noise in the system. In this case, we're using a signal to noise ratio of 24 dB, which is what you may encounter at the sensitivity point of 54 megabits per second. And here we show the scatter diagram of the pilots. Even though we are doing carrier offset estimation and correction, the carrier offset is very large, it's 100 kilohertz. So most of the carrier offset has been effectively eliminated, removed. However, due to the noise, there is a residual carrier offset. We are also simulating over a large packet size, 4,000 bytes. As you know, the maximum length for packet size is 4096, 2 to the 12 bytes. And you can see that the residual, because of the noise, the residual carrier offset still exists. And here we're turning the block that corrects for pilot tracking is turned off. And we observe that, in fact, the residual carrier offset causes the pilots to rotate. In the next diagram, you see that the whole constellation has become distorted and we have intercarrier interference, and of course a complete failure in packet detection. In the diagram on the right, we have the constellation with pilot tracking turned on. In this case, the pilots are correcting for any residual carrier offset, and we see that the pilots are in fact forced into their correct position, and this tracking operation applied to all the carriers within the 48 data carriers, we see that the constellation is then corrected and intercarrier interference has been eliminated, and we're just left with the noise in the constellation.